thank you all for coming, and of course, thanks to the organizing committee. Special thanks, it was at FPSAC last year when some very insightful questions from Adriana Garcia got me started on basically everything you're going to see here tonight. So I certainly owe a lot to FPSAC and, of course, Adriana. The rough outline is that we're going to start with some preliminaries really quickly to make sure we all have the same notational conventions. And then I'm going to get to the results in terms of symmetric functions as quickly as possible. Then we'll bounce back and talk about the machinery that actually created those results, in particular dual equivalence graphs. So my diagrams will be in French notation, but in particular, my diagrams will also be subsets of Z by Z. When I use the word diagram as opposed to partition, that's what I mean. And a bit that you might not know, pistils. To find a pistil, you take a cell, you take all the cells in the row reading word until you get to the cell directly below it. That set of cells is called a pistil, or it's attacking cells plus 1, if that makes you feel more comfortable. Okay, so these define the pistils. Of course, we've got our standard Young tableau and our semi-standard Young tableau, and my reading words will always be row reading words. Also, we've got our familiar content monomial x to the t that we get from a tableau. This signature you may not be familiar with. It's basically your inverse descent set. So if I have a permutation, I take the signature of it into sequences of pluses and minuses where I get a plus if I precedes I plus 1. It's the inverse descent set just coded up with pluses and minuses. And if I want the signature of a filling that happens to be bijective, then I just take the signature of the row reading. So nothing too fancy there, I hope. Of course, I have my sure functions as a generating function over semi-standard Young tableau. But if I want to rewrite this in terms of standard Young tableau, I'm going to go ahead and use my fundamental quasi-symmetric functions that I'll denote f, and they're indexed by some signature, some inverse descent set. So in particular, there are two standard Young tableau of shape 2, 1, and I can then write my sure function 2, 1 as a sum over f with the two signatures of those tableau. That gives me a nice finite set to sum. Of course, we care about sure functions for lots of reasons, including physics and enumeration and Schur calculus and representation theory. But just to draw your attention to one that you may or may not know, in the case of the Hall-Littlewood polynomials, that thing on the left, if I expand that into sure functions, by the way, that's my modified Hall-Littlewood polynomial. If I expand that, my coefficients are my Koska-Folks polynomial, and those give irreducible characters of GLN FT representations, where T is a prime. So that's kind of neat. You get a polynomial. Then you decide what prime you want, so you plug it in, and this gives you your irreducible characters. So we care about this, and traditionally, this is given to you by the cocharge statistic by Lescu and Schussen-Berger. One of the main results of today is actually a different expansion for it, using a subset of the Yamanouchi words. And we'll go ahead and spend a lot of time talking about what all those symbols up there mean. In fact, we're going to give a more general version than this, but this is kind of a key punchline for today's talk, is this different expansion. So, to get into what this result is, we have to back up. What are McDonald polynomials? Well, there's algebraic definitions, but I really like the combinatorial one by Haglund, Hinman, and Lohr from 2005. So, all right, is everything okay? So I'm going to go ahead and just use this as my definition, basically, for my modified McDonald polynomials. And in this case, indexed by a partition. In case you don't know, right? McDonald polynomials are really important. They specialize to all kinds of important other symmetric functions. And they show up in geometry, algebra, and also in physical applications. So if you want to know more about those, you can ask me later. I'll point you in the right direction. Okay, but for me, like I said earlier, I want to talk about diagrams. I want to generalize to diagrams. The generalizations I'm going to give are strictly combinatorial. I have no idea what they mean algebraically, so feel free, if that's really your thing, to work on what might these generalizations mean algebraically. But they do agree with the partition definitions. So we'll cover all of those stats you just saw on the last page via these diagrams. So a descent set of a filling of a diagram is just the set of cells where the value in it is bigger than the cell below it. Okay, so 9 is bigger than 8, 7 is bigger than 6, so those two bullets represent my two descents. And then if I want to find the MAJ, all I do is for each descent, I count the cells weakly above and in the same column, and then I add these numbers together. So there's one cell above the first bullet, there's two cells above the second, and that gives 3. And this is my nice generalization to any diagram of the MAJ statistic. Okay. If I want to go ahead and talk about IMV, I need to talk about a triple. So a triple looks like this. I have two cells, one on top of the other, and a third cell off to the right in the first row of those two. And an inversion triple, I promise not to test you on this later, is an inversion triple is a triple that is filled such that it has a decreasing orientation clockwise. So in this case, the second 7 is considered bigger than the first 7 because it's latter in the row reading order. So 7, 7, 4 in the clockwise direction is considered decreasing, and so this counts as my only inversion triple for that filling. I then need inversion pairs. So an inversion pair is if I'm missing one of the two cells on the left, I suppose I could use the laser. If I'm missing one of the two cells on the left, then I just say, are my values decreasing in row reading order? If it is, that counts as an inversion pair. Those are my two inversion pairs, and then I kind of made up a third one because there aren't any of that shape in this example. So that then gives me the imp statistic for any diagram. There's one triple, two pairs, 3 is my total. If you like, take your diagram, add zeros on all the missing cells, and then it'll be your old imp statistic for a partition. So it's nothing too crazy. It agrees really nicely with your LLT interpretation if you like thinking of McDonald's as the sums of LLTs. Okay. So as I said, I promise not to test you on this, but I wanted you to at least know there's nothing too crazy going on with these statistics on diagrams.
If there's one thing I should remember about all that?
If there's one thing that...
it's not too crazy.
Okay.
Sure. Actually, there's another thing you should remember.
Great.
Just to back up, your match statistic is only dependent on the descent set and the shape and the diagram itself. So if you wanted to make other generalizations, you actually could redefine MASH to your heart's content, so long as it's only dependent on the descent set and the diagram. Hopefully you want it to also agree with the definition for partitions as well, but there's room to play with that as well. So, thanks, Ben. So now I can go ahead and define this generalization of McDonald polynomials. Like I said, it's strictly combinatorial, but it works for any diagram. And I want to do this because, well, it's neat, and because it actually helps the proofs go, you'll see in a little bit, and the results work here. If I want to write this using quasi-symmetric functions, then I can go ahead and just think of bijective fillings or fillings whose reading orders are permutations. And I'll use my fundamentals in there instead. So combinatorially, this is what I'm actually going to play with the most. Okay, so now this lets me define my modified Hall-Littlewood polynomials, the things we care about for this talk the most. That's just when I set q equal to 0. So q is 0, that means I need no inversions, and that's all you're seeing here is that I'm not going to allow any inversions on those fillings. And then I'm going to go ahead and define this thing that I think I made up, but if anyone here has claim to it, do let me know. This R is a refinement polynomial, so we're going to fix a descent set. Since the descent set determines your match statistic, we can then drop the t. So now this is just a function in my x variable. Okay? And it's easy to see if you know all of your R's, then you can recover your Hall-Littlewood very naturally. Fun fact, why you might care about R, if you're one of these people who collects generalizations of Schur functions. R lambda lambda is your Schur function, so there's another. And then the question, of course, is, well, what are the Schur expansions of these things? When do we have them? I can't get them all the time for McDonald's, but maybe we can do better for the Hall-Littlewood and for these refinement polynomials. And that's going to be a question of collecting these monomials into Schur functions. All right.
Are they symmetric functions?
Are they? Well, a priori, I don't know, but the answer is yes. Yes, they are. Because in a second, I'm going to give you the Schur expansion. So,
any diagram.
yes, for any diagram, they're symmetric functions. It's not too hard to prove with some previously known results, but I'll give you the Schur expansion in a second. So that's what's counted. Okay. So I need to quickly define a couple things. Yamanouchi words are familiar to a lot of you, but just to remind you, a Yamanouchi word is a word that when read backwards has weakly more 1s than 2s, more 2s than 3s, and so on and so forth. So if I want to make all of them, I often will make a tree. And I'll start with the number 1, and I'll append numbers to the left. So next I could add a 1 or a 2, and then I could continue on this tree, and the point is that I could not have 1, 1, 3, because then there'd be more 2s than 3s, and I could not have 1, 2, 2, because then there'd be more 2s than 1s. And then you continue making this tree until you have as many values as you want for your filling, right? N. Right? Then I'm going to go ahead and call yam lambda. It's a set of Yamanouchi words with lambda I many i's. talking about the content. SYAM lambda is the set of permutations given by standardizing that. So in particular, YAM22 has 2 1s and 2 2s on both of those. SYAM, I've just taken the 2 1s and I turned into 1 2. I took the 2 2s, I turned it into 3 4. And the fun note is that when you standardize, you're preserving your imb and your maj and your descent sets. So it behaves nicely with respect to that.
But standardizing means that you standardize in the...
Yes, left to right order. Yes. Opposite of the way you build your Yamanouchi works. Unfortunately, but true. Okay. Now the really long definition for the talk. Just bear with me, I'll get you through it. So, if T has shape delta and its reading word is W is a Yamanouchi word, we say that W jams delta if when read backwards there is some I and J such that the jth I and the J plus 1 I plus 1 share a pistol. Furthermore, my non-jamming Yamanouchi words, yam delta, are going to be my Yamanouchi words that don't do that, that don't jam anything. So, let's go through this step by step. Oh good, the colors are showing up. Can you all see the red and the blue?
Yeah.
I'm so happy for whoever fixed that. Thank you, organizers. So, as you can see, here's the first one, here's the second two. Right? Here's the second one, here's the third two. Here's the third one, here's the fourth two. Right? That's this jth I and j plus 1 I plus 1. Right? Here's the first two and the second three. So you just think about all of these pairs. That's that pairing, this jth I and this j plus 1 I plus 1. And we want to ask, are they in a pistol together? So what do I mean by that? I mean, well, think of this word as the row reading word. And then you say, are they in a pistol? So on that second row, you see that that 1 and that 2 are in fact sharing a pistol together, and that 3 and that 2 are sharing a pistol together. In this case, we say that those pairs jam the pistol. Thus the word jam. Yeah. Okay. Thanks. And then the Yamanouchi words that don't do that, those are the ones we're going to keep. Those are my non-jamming Yamanouchi words up top. Okay? So with that in mind, miraculously, we can now express my modified Hall-Littlewoods and my refined Hall-Littlewoods, my refined polynomials as these sums over my non-jamming Yamanouchi words with no inversions, or my non-jamming Yamanouchi words with no inversions and a particular descent set. So in fact, this then answers your question, are they symmetric? Well, yes, and they're sure positive. And in fact, there's a nice bijective expansion for their sure positivity. So I think that's really nice. So reasons why I think that's really nice include this. So if I think about finding all my non-jamming Yamanouchi words, one thing you'll notice is that you can continue to make a tree, and as you think about adding your next number, you can check, is it still Yamanouchi? But you can also just as easily check, have I jammed any pistols? Right? And you can think, have I added any inversions? And if you do at each step, well then you totally killed that branch of your tree. So you can still enumerate all of these by making a tree, which leads to lots of nice combinatorics. And this is meant to go ahead and demonstrate some of that nice combinatorics. If I want to think of a 3-row shape, I think about all the ways I can fill this. And in fact, think of a much bigger shape, and you're just worrying about the first 3 rows while making this tree. Those first 3 rows can go really fast, because you know it's inversionless in Yamanouchi, so you have to have all 1s on the bottom. And then you know the second row has to be some 2s, and then some 1s. Okay? And then you know, using all 3 of these properties together, that the first 3 rows have to look something like this, so you could even skip massive parts of this tree, because you know what those first 3 rows have to look like. And if you're really patient, you can go ahead and think about what the first 4 rows have to look like, and so on and so forth. And it leads to this really nice description and really pretty fast algorithms for getting all of these coefficients. It also leads to some nice combinatorics in that, especially just think about 3-row shapes. I can start writing these coefficients using your fun binomial coefficients and factorials when I start thinking of it this way. So it really lends itself to some nice proofs as well as some nice just discrete geometry kind of situations.
So what are these
Oh,
fillings actually?
so this is sort of the first 3 rows of any, if I want to think about my non-jamming Yamanouchi word, my non-jamming Yamanouchi fillings with no inversions, and I want to think about making these backwards from the bottom row, filling them right to left, and the second row right to left. They have to look like one of these 3. The first row would have to be all 1s.
How do the rows come about?
How do these, so if I want to, it's Yamanouchi, so it has to end in a 1. Then it has to have no inversions. So because it has no inversions, that's going to force this whole first row to be all 1s. Okay, and then it still has to be Yamanouchi, so you're going to have some 1s and then some 2s. But then thinking about no inversions, that's going to force everything left of it to also be 2s. And then you get to the third row and you get some slightly more complicated analysis using your non-jamming. And it forces you to look like one of these three things when you're filling up those first three rows of any filling. Okay, just by letting all those three properties play together. And then you can move on to if you had a fourth row or fifth row. You guys are making this tree. Higher up means farther to the left in your row reading word. Right. Does that clarify?
There were more things after you'd written down the first two rows. For example,
Right.
you would have had more stuff to level above. Then you proved them all off at this point.
Right. So if I was making a tree of all the possible fillings of say a 4-row shape, you'd start by thinking about how to fill my first 3 rows.
Yeah.
Right. And then you think about what could go into your 4th row or 5th row. Is that no?
I was just gonna comment, you're basically sort of like minimally, or maximally unstandardizing here, right? Like
Right.
the sense
So
of being the same
it's
place.
much easier for me to talk about the algorithm for finding Yamanouchi words than standardized Yamanouchi words. But you could play in the standard line if you want to. But yes, Yamanouchi words are your maximally unstandardized fillings. Absolutely. That's a great way to think about it. In fact, if you read the paper, I think there's an unst operator that does that. Here's another reason, another reason to care, at least a good conjectures. So if I take my McDonald polynomials, I haven't given you a sure expansion for those. You can get it in some cases, but in general, there's this nice conjecture, which is that if I take my McDonald and I subtract off everything I get by just looking at my non-jamming Yamanouchi words, I think that thing is still sure positive. Seems about right. I checked it for partition shapes up to, I think, degree 9. That's a pretty good number. If I think of this another way, it says, well, there should be some function that takes my jammed Yamanouchi words and it just moves them a little bit to some other word that fixes the rest of this polynomial, giving you a full expansion. That I should have some function that leaves my non-jamming Yamanouchi words where they are and moves everything that's jammed a little bit over to get the correct statistics. And if this really interests you, then you can talk to me later when I have more than 25 minutes. Okay. So, where do these results come from? They come from an area that I care about just as much as I care about these sure expansions. That's dual equivalence graphs. So the natural question is, okay, what's a dual equivalence graph? The answer is, well, those are dual equivalence graphs. As are those. So you'll notice they can have double edges but not triple edges. You'll notice that sometimes they look like puppy dog faces. And you'll also notice they have a lot of internal structure. They have a lot of internal symmetries, right? These are not random graphs. There's a lot going on, forcing them to take certain shapes. So if I want to generate all of my possible dual equivalence graphs, then you need to know what an elementary dual equivalence is. And I'm going to go ahead and say, ignore that definition, look down here, and say the way that D4 acts is it looks at the numbers 3, 4, and 5. It says 4 is in the middle, so do nothing at all. The way D2 acts is it looks at the numbers 1, 2, and 3. It says 2 is not in the middle, so leave 1 in the middle and flip the 2 and the 3. And the way D3 acts is it says, look at the numbers 2, 3, and 4. 3 is not in the middle, so leave the 2 in the middle and switch the 3 and the 4. If this looks a little bit like a weird Knuth equivalence, that's because dual is short for dual Knuth equivalence. Okay? So that's the way this acts, and it's a result of Heyman, but really it also follows pretty straightforwardly from Lascaux and Chusson-Berger, that dual equivalence acts transitively by row reading words on standard Young tableau of a given shape, of a fixed shape. And then what Sami Asap did in 2007 is she turned this into a graph structure. And she said, okay, let's let D4 act on a standard Young tableau and label this edge by a 4. Okay? And she also attached signatures to each vertex. Okay? And then the transitivity says that each component is going to correspond to all of the standard Young tableau of a fixed shape. That's what that transitivity provides you. So the nice result then is that I can replace this definition of sure functions over a standard Young tableau with the vertex set of a standard dual equivalence graph. And that's what I'm going to use for those particular graphs formed in that way. Those are the standard ones, G lambda. Right? That's just a trivial substitution there for my standard Young tableau. To talk about what is the structure of this thing, to back up just a little bit. So a signed colored graph is just a graph with labeled edges and some signatures attached to the vertices. And then I can define what is a dual equivalence graph in general, and saying it's any signed colored graph whose components are isomorphic to standard dual equivalence graphs. Okay? And then the crucial point here is that if I have a dual equivalence graph with 2 components isomorphic to G mu and 3 components isomorphic to G nu, and then I sum over the vertex set with these fundamentals, well then I'm going to get 2 times S mu plus 3 times S mu. And the game is always going to be take a function, associate it to a dual equivalence graph, and then sum over its isomorphism types to get the shear expansion. So, we don't really like to think about finding isomorphism types of graphs and deciding whether or not they correspond to standard dual equivalence graphs, because isomorphisms are hard, right? For anyone who does graph theory. So there's this theorem, Sami Asaf kind of did one direction and I did the other, so it's really 2 theorems put together, that a sign color graph is a dual equivalence graph if and only if it satisfies 2 nice properties. So one is that restricting to 4 consecutive edge colors gives a dual equivalence graph, and the other is that edges that differ by more than 2 commute, easier to do by pictures. So here's 2 edges commuting. I and I minus 3 share a vertex, so then they make a box. Okay? Here are all of the possible ways that you can get a dual equivalence graph by connected dual equivalence graph by looking at 4 consecutive edges. So if I restrict to 4 consecutive edge colors, then I should get one of these shapes. And that's it. Make boxes, get these shapes. And what's great about that is that I can be really stupid and let a computer check this. Right? These are local properties. So as long as I know what an arbitrary vertex looks like, or I can restrict to a certain set of arbitrary vertices and how the graph around them looks locally, well then I can sort of guess graph structures and let the computer tell me if I've done something really smart or really dumb. Okay. That's, in my opinion, really nice. So, what's the graph structure I should be using for McDonald's? Well, Sami Asaf came up with this nice construction that I only mildly generalized. Capital DI, and all it does is it says, if I minus 1, I plus 1 are not in a single pistol, then do this DI we like. And if they are in a single pistol, if they're close together, then do DI tilde, which I'm not going to define for you, but is just a cycle instead of a swap. Okay. And the fun thing about this, why you would do this, is that capital D preserves your descent set, your im, and your maj, and you let this act on those fillings. It's exactly what you would want, because the next thing you're going to do is go ahead and define that graph structure by letting your vertex set be all of your permutations, letting your signature function be exactly what it was before, and letting your edge sets be defined by this capital DI instead of that lowercase di that we had for our standard dual equivalence graphs. And then the fun property holds through that my descents, my imp, and my maj are constant on each component. Okay, so what that buys you then is that each component that's associated to a shear function also has a constant statistic attached to it, my q to the m, t to the max. All right, so then what do these look like? Well, sometimes at top they actually are dual equivalence graphs, but often they're not. Often there are lots of other things that make for great Rorschach tests. But there's a lot of them. I'm pretty sure that one is a snail with a metal detector. That's what I decided originally. Okay. But sometimes they are dual equivalence graphs. So in particular, the whole ASAP graph is a dual equivalence graph if and only if delta has no pistons that contain more than 3 cells. And in that case, you actually get the expansion of the McDonald polynomials directly. More remarkably, more amazingly, totally fell into my lap without me being too smart at all. If I restricted components with no inversions, it's always a dual equivalence graph on its own. Just like just mana from the heavens, right? Just, because I was able to use that isomorphism check from before, right? Because I didn't have to do anything too smart, I just used that classification. I was able to just check what does an inverse filling look like, and this came out right away. Okay. Morally, what this tells you is that my expansion for my Hall-Littlewoods should be a sum over components, where I take that constant match statistic on each component, and the isomorphism type of that component gives you which shear function to attach to. So we still don't like checking for isomorphism types of graphs. This is still a really painful thing, so we'd like something better. And luckily for us, we get something better. This one did not fall in my lap. This was lots and lots of work. So if you read through the proof, sorry. So if G is a connected dual equivalence graph inside of an ASAP graph, and you know that it's isomorphic to G lambda, well then we have this indicator vertex that says it's isomorphic to G lambda if and only if or it has a unique element in our non-jamming Yamanouchis. And furthermore, oh, I kind of said that differently than I wrote, right? Of that given type. So what this non-jamming Yamanouchi word is saying is, if it's there, well then that lambda is the isomorphism type of that component. And furthermore, there's only one, so you're not overcounting anything, right? That's a nice if and only if. And that's what lets us go ahead and give this expansion, because now instead of summing over components, we're summing over those representative vertices for each component. And that's why this all works in this nice diagram setting, and of course why it also works for the finite polynomial. Well, there's a couple of other results in the paper, and there's actually lots and lots of open questions and conjectures in the paper, if you read the full one on the archive. We give a simple method for finding the leading term in the shear expansion of that finite polynomial. We classify when our McDonald's and our Hall-Littlewoods are expandable over just the Yamanouchi words, as opposed to the non-jamming Yamanouchi words. And we give equivalent results for polynomials that maximize m instead of making them 0, amongst some other things. So if you like that, please do check it out on the archive. Other than that, thanks for listening.
Questions for Austin?
Do you have expansion of these H delta in terms of the usual McDonald HV? So you have a diagonal.
So if I have, right, because McDonald's are on an orthogonal basis, right? So there should be expansion when they're not a partition. And the answer is no, not at all. But that would be very interesting and possibly challenging.
Also, have you tried expanding these R's in other bases like the E, for instance?
Right.
It would be interesting if there were E positive.
Right, well, as mentioned, some of the R's correspond to shear functions, right? So anything,
Okay.
right, anything that's going to be difficult, right? Yeah, but there might be special cases in which they do.
Do you have any pictures? Excuse me.
Any pictures?
Of these delta
Values.
that you're gonna show them?
Of delta?
Yeah, can you show them again, or is there any way?
Of just delta is just any subset of the z by z Cartesian plane. So I think I started off with one really early, right? And then I kind of stuck to partitions. It's a lot of slides, sorry.
And that-
No,
what you
it's
have-
not over to There.
There you go. Right, so there's one, but it's nothing in particular, right? Just any subset.
I'm very curious about these shapes. I wonder if they are related to the science fiction. I just wonder.
Are you thinking of papers with Francois?
Francois.
I must admit that this is on my list of things to work through more thoroughly.
That would
It's
be
a very
really amazing.
intelligent paper, and takes a little time to digest all the details. So, but it's definitely on my things that I'm going to think about more. Absolutely. So, in case you don't know, there's a paper that deals with, in particular, moving cells.
There's a number of conjectures there that nobody's touched.
Yeah.
It's a really beautiful conjecture, actually.
Yeah, well, one of the reasons why I did diagrams instead of partitions is because you're dealing with fillings of partitions, and if you want to do any kind of recursive proof, you need to be able to remove a cell. So, yeah, so then everything kind of fell from there.
There's a question.
How do you know about any complexity bounds or memory bounds to get these non-jamming words?
Right, so Hari is a really good guy to talk about. So Yamanouchi words in general are exponential time. So you can do it in exponential time for sure, because you're not actually adding much more complexity than any of those algorithms, right? But the short answer is no, right? It's not going to be much faster than Yamanouchi words unless you're more clever than me, which you might be. Yeah.
If you expand your generalized H delta Hall-Littlewoods in terms of shear, do you get a natural analog with like co-charge type formula for particles?
So you should get the same polynomial, right? The cocharge. Oh no. So here's the issue: is that for the partition case, you're going to get the same polynomial. So that's a very direct analog. I don't know. So I don't know what other way to generalize sort of my cocharge outside of this. So, right when you think about code charts, there's sort of partition shapes all over that definition.
Yeah, I was
So-
just seeing if you could generalize it to these
Right.
general things.
Feel free to try. Yeah.
I have another question. When you take t equal q equal 1, Macdonald polynomial,
You get Yamanouchi.
one to the n, because the Macdonald polynomials are bigraded version of the left regular representation. Is this the same case? You get the same e1 to the n for a general
So
delta?
if you take t equals q equals 1,
Yeah.
right? Well, then the sum you're going to get it will be a sum over Yamanouchi words, right? So we've ignored we removed the im equals 0 condition entirely, right? So you don't need any jamming condition for that case. It's going to be equal to just the sum over your Yamanouchi words, and you don't need anything super
But
fancy.
how many?
That's,
All of them, right?
Except
So it should be equal to
Yeah, it's
e1 to the n.
right.
Okay, so they're all must be bigraded versions of the left regular representation.
Right, so if you can figure out what it would actually be, that would be great. But knowing what that representation is, right?
In many of our science fiction constructions, they are migrated versions of the left representation.
Right,
That
so
would be very nice.
it would be fantastic, and I would love it if someone would do that.
All right, if you have more questions for Austin, you can ask him during the break between now and the poster session, which is in 15 minutes. Let's